Hauke will tell you better how it goes. This is sounding louder, isn't it? So, Hauke is the professor from the Institute in Geotechnical Engineering at the University of Darmstadt, Technical University of Darmstadt. And he will present you with another flavor of a similar approach. So in this case, it's not centrifuge modeling, is more on field scale modeling. So how you deal with the design and data collection of a large scale model. So everything is ready. Thank you, Hauke. The floor is yours.
So thank you, Miguel, and thank you, Luc, for being perfectly in time. So I was not expecting that. Yeah, what are we going to do? I'm going to speak to you today about large-scale modeling in geotechnics. And so it's somewhere in between. So the field testing will be presented by Lee. And so we are here now. Yeah, so we thought about a short bio break, but I think for the sake of time, we're going to skip that. We're going to speak now about this large-scale physical modeling. And the introduction is I'm going to give you a very brief introduction into our test pit. And based on that, I'm going to talk you through the process of modeling in a larger scale. Although we can skip or go very quickly over these points because you saw almost everything today in miniature for the centrifuge. So in our case, everything is a bit larger. It takes much longer. It's much more effort, but the questions you have are always the same. So how can I place a proper sand model or soil model? How can I place my sensors? Which types of sensors do I need? How do I scale my model? It still is the same. Yeah. So that's why we're going a little bit faster through it. And we have two exercises included. Here's written 15 minutes, but we will make them shorter. And for that, I want you to pair into groups. Yeah, so I want to create two groups so that you can rather discuss. The one exercise needs some calculation a little bit, but yeah, you can just be into groups and then we can discuss the results. Did everyone receive the email with the data and the presentation this morning? Yes? Anyone not? You're not. So, okay, so you are not in that email list. So you also didn't have the email from Luc. Okay, so we have to fix that. Yeah, so please come off. Better you send Miguel an email so that he can include you to this mailing list. Yeah, because my problem is, or you can do it straight, Eva, thank you. My problem is, or my concern is my boundary condition. I have to leave, unfortunately, at a few minutes after 6, because then I have to get a train back. So I will not be here for many questions afterwards. So if you want anything, then please just put it in between. So yeah, let's do it quickly. So geotechnical modeling in the test pit. I just want to briefly introduce you to our test pit. What do we have here? We have a large scale test pit, which is 20 meters long, 5 meters wide. And we have two areas. One area is the so-called deep part with about 6 meter depth, and another area with about 3 meter depth. Yeah, we have loading rigs, which we can apply everywhere here where you see these points on along the pit. We have such walls which we can use to separate, to make smaller sections. Yeah, and yeah, our loading rigs, our loading frames can also be inclined. So like you see it here, so we can have horizontal, vertical, or inclined loading. We have different actuators. Maximum capacity is 200 tons. So it's quite large, like you see. And now, of course, what we need to do is the same like you do in the centrifuge. So first is sample preparation method. And so Yannis, you asked how our RAINA looks like. So this is how our RAINA looks like. So it's not as automated as we have it here. We would like to have it, but let's have a look. So the principle is the same. Yeah, we pluviate our sand into our system, and you see here the box which is containing the sand, and then the sand falls here in those 4 pipes, and here we have a cone. You can see the cone here, and on this cone, the sand then hits the cone and then it's distributed. And by that we achieve pretty good homogeneous samples. Although, of course, this crane is this sand RAINA is operated by hand with a crane. Yeah, so and of course then you have the issues like you learned today. So if you turn around, yeah, then you don't have a proper soil density there. But that's also why we always try then to be sufficiently far away from our model, and then we don't have a big issue there. What you see in even bigger pits is that often people rely on simply this moist, let's say moist tamping, but in large scale. So that means you just layer-wise compaction with your soil, often also really moist, and then you get such a distribution here of the tip resistance, for example, with the CPT. So this is not in our pit, this is in another pit, like I said, with the layer-wise compaction. Sometimes, and I saw that Zachert, for example, is doing that, they have fluidization, so they just put the material there, have it in a loose condition, and then they densify it, yeah, with vibration. So typically, like I said, the control of your density is done by CPTs. Next thing for us, which is important, and since we target our training and this workshop here so that it's all related to piles, of course we need to consider how does our pile finally comes to the soil model. And here you have which is a small presentation on. This is on the left-hand side how you do it in several numerical studies. So your pile is wished in place and the soil conditions around it are not disturbed at all by the pile in the initial situation. And this is if the pile is only jacked a few centimeters here in this case. And you can see that immediately, of course, your stresses change significantly. And this is something you would also want to have it in your model, or you want to have it out. It depends on what you want to model. This is what Luc said earlier in the introduction. You have to construct your model such that it really reflects what you want to model. So which type of pile installations do you have? So in many cases, we do wished in place because that's the easiest we can model also in our numerical models. So that means you simply place your pile and then you pluviate your sand or install your sand around it. I will mainly focus here on sand because large-scale testing in clay is even harder because then you have to prepare large clay bricks and bring them to your pit and so on. So again, Zachert, for example, can do that. We in Darmstadt, we don't have such a device. This is it's an incredible device, but it's also incredibly a lot of work. So the next thing is you install your sand sample and then you push your pile, or so this is an example of pushing, or impact driving, or with vibration. Yeah, so you have all those typical pile installation methods. You can also use them in our scale, of course. The nice thing here in our scale is that we don't need to have miniature actuators to put them in, but we need something in between the real scale and the large scale, as the real scale and the centrifuge scale. But of course, here you should only do that if you also want to apply this or to model the effect of this installation. Yeah, or you have to take that into account then. So, and of course, you could also use other things like screwing piles or have such a board pile. With such a small rig, you could enter our pit and you could even install a board pile in our system. So that's at least feasible. Then, of course, you have all these sensors and equipments, and we discussed about that, or you learned already a lot about that. On the left-hand side, we have the classical ones, so like LVDTs or force sensors or force cells and so on. Of course, we also have pressure cells, but I think it depends on whether you already work in geotechnical modeling. You will find out that nowadays a lot is done with fiber optics. and they are really very, very powerful to really measure strains, not just on one spot, but over long areas. So this is a nice technique. And a very important part of preparing your models is choosing the right dimensions. And there are a few points. So the one thing is scaling. Yeah, of course, you have to scale your model such that it matches with your requirements. And I think you heard already a lot today about scaling for the centrifuge. And now let's have a look whether it's really different for the 1G testing. And the other one is that you need to take care that you are not hitting your boundaries, that you don't have a boundary effect. So there are different ways of scaling. The one is purely geometrical. This is what you see here. So this is really, you purely look at the geometry and then you scale everything down. Also the velocity, the acceleration, the forces, and with some factors. Yeah, like Luc already showed it in the presentation in the beginning. But this is typically neglecting the effect of the stiffness of the pile. Yeah, so and of the soil structure interaction. So if you purely follow this, then you will not really get what you want. You don't get the proper representation of your model in your of your large-scale test, in situ test, in your model test. So I would not recommend to do it with purely geometric scaling. Better is that you look at the laws of similitude after Wood, 2004 here. And here I have a nice example, which I think it really demonstrates it very, very well. This was in our joint presentation, and I have to not to claim things which are not done in Darmstadt. So this has not been done in Darmstadt. This has been done in Hanover. There, they tested 3 different piles. Yeah, and these 3 different piles, you see, they have different diameters. Here we have the reference pile, and here we have the other diameters. So you can see between 600 millimeters and 1.2 meter in diameter. They all have the same steel strength. And here, this is our in situ pile. So the monopile has 8 meters in diameter, an embedment length or penetration length of 32 meters. Yeah, and now they have 3 different piles, and they were all scaled according to different laws. Yeah, so let's look here on these pies here. We have the dimensionless. So okay, how can I explain that? Maybe no. Okay, so if you purely look at the diameter, this is not always or on the force. This is not always representative. You should look on the ratio, for example, of your penetration depths to your diameter, or of your penetration depths to your elastic length of the pile. By the way, can anyone explain me what the elastic length of a pile is? What is it? Have you heard about that? It's something here. It's written here. Maybe if you see this formula, then maybe you remember that. Okay, so this elastic length, this gives you an idea about whether your pile is stiff in comparison to the soil or whether it's flexible, so how it behaves in the soil. So this elastic length also includes the stiffness of the soil by this factor K. So this is your bedding reaction of the pile. And this, for example, I guess you know that if you have a pile and you load it horizontally, and if it's, let's say it's 8 meters long and you load it horizontally, you get a certain displacement at the pile head. And then if you make the pile longer and longer and longer, at a certain point, your response does not change anymore. Yeah, because everything which counts is happening here on the top of your system, but the length of your pile does not have any impact any longer. So this is how you determine this elastic length. And of course, this is a difference. If your pile is very stiff and you have a soft soil, then this elastic length, so then your impact is much longer than if you have, for example, a very flexible pile and a very stiff soil, then you have only a very small elastic length here on the top. Yeah. So considering these aspects is crucial for having really a representative model. Yeah. So that's the elastic length. And here you can see that, for example, this real pile has an elastic length ratio to the real penetration depth of 0.64. So this pile is deviating from that. The other both are matching with that. Here with the penetration to depth, there we have this pile, which is different to the others, but the other both are matching with this. So, and this is how you can also scale your horizontal force, your moment, and also your expected deformation. So, for example, here this horizontal force is also typically then represented in relation to the length, your stiffness, and your weight, and so on, because then it makes it more comparable. Yeah. So, and these three piles now, you see with some different dimensions, different wall thickness, and so on, they have been tested. And on the left-hand side, you see the nominal result. So you have the horizontal load over the horizontal displacement, and of course, to be expected, yeah, the smaller pile has much more deformation than the bigger pile. Okay, this is expected. But now, which is nice, if you compare them to the normalized horizontal load according to this equation here, and you put it in relation to the normalized displacement with it, which is normalized with the length of the penetration of the pile, then you see that all these three piles behave more or less the same. So this gives you a good impression that you don't really need to do a test with a 1.2 meter diameter pile. If you consider the scaling laws properly, you can also do this test with the 600 millimeter pile and save some money, some time, and some space. Yeah. So this is important. Okay, any questions on that? Okay, so have these laws in mind. They are really they are good for scaling in 1G. And yeah, next thing is, of course, we have to avoid any boundary effects. So if we have a pile here and we want to load it, and yeah, what do you think? So how could you determine a good distance to your boundary? What do you think? How would you do that? Let's assume we want to perform again a horizontal loaded pile test here. What would you do now? Sorry?
Passive resistance to the soil.
Yeah, you can look for the passive resistance. Yeah, that's good. Anything else? Numerical analysis. Yeah, I mean, nowadays it's not really a big thing to do just a numerical simulation. And before I start such a big test, which costs you several months of preparation and performing, well, it depends on, yeah, but at least it will be a few weeks. In our case, for one such a test, we have to place about 70, 80 cubic meter of sand. Yeah, and to pluviate 80 cubic meter of sand is not fun. Yeah, you saw it. You really demonstrated it very nice. So how to pluviate sand really thoroughly, and that's the same if you do it in large scale. Yeah, of course, then you cannot do it manually, but still you stand there and there's a lot of a lot of dust and so on. So yeah, you do a numerical analysis. That's good. Here are some recommendations from a publication which are saying, okay, you need to have at least 3.5 diameter of your pile as distance to the boundaries, but I do not fully recommend these. Yeah, so I go quickly to the next one and said, okay, like you said, so look at the passive wedge, for example, the passive earth resistance, or you better do a numerical analysis. Because if you are, for example, only looking at the yeah, for example, do a high cyclic loading or so, and you're not pushing your pile until failure, then the region which you're going to occupy with your test is much smaller. Yeah, you can probably even allow a bit smaller pit than if you really want to push your pile to the end. Yeah. Okay, another one, and this is what I recommend you if you don't have the time, if you want to do a proper first analysis, you can look at such building codes as well. We have here the recommendation for pile groups. And pile groups, there you know that one pile is affecting the other. And there's, from this German standard, there's this nice picture, and this gives you a relation between the factor, how much one pile is affecting the other, and the distance between those two piles. And here you see that there is a factor of 6, so 6 times the pile diameter. Then in such a pile group, you don't have that much impact. Yeah, of course, this is not this is for a building practice, but nevertheless, this shows you, okay, 3 times the pile diameter is probably a bit small. Better use 6 times the pile diameter as a distance. Yeah, and that, I would say, these 6 times, that really gives you a good feeling of how much the distance to your pit should be, to your boundaries should be. If you have a shallow foundation, of course, then you look at the wedge here of your failure. Okay, so I suggest we do a first small exercise here, and in this exercise, so I skipped the data processing, and we're going to speak about that then later. And in this first exercise, let me see whether I have it here. Yeah. Here we have it. So this is your exercise. Yeah, we have a prototype. We have a pile that has a diameter of 2 meters, a length, penetration length of 8 meters, and a wall thickness of 30 millimeters. And we have our test pit dimensions, which are given. We have a deep part and a shallow part, and we have the test material, which is a medium dense to dense dry sand. And our pile installation is wished in place. Yeah, so that means we install our pile and then we pluviate around it. And what do we want to investigate? Yeah, we want to investigate the development of the bending moments in the pile during horizontal cyclic loading. Yeah, so we're going to look at the bending moments. That's our aim. And we want to apply cyclic loading with a load factor which is about 30% of the ultimate load. Second thing is we want to determine the stress development in the vicinity of the pile, so what is happening around the pile. And the test should form a basis for numerical simulations to validate constitutive soil models. So this is our idea. This is why we perform this test, okay? And now you have two tasks, and I suggest that we really make 2 groups, so you please sit together and really discuss. I mean, it's a big group here, so okay, we do it the other way around. Is anyone involved in his or her PhD in pile testing or modeling? Yeah, you. I know you. Last time you you gave the perfect answer, so so you are not allowed to contribute this time. So no one. Okay, so everyone has the same conditions, so that's very good. So I suggest then that we really make 2 groups, yeah, and probably we just divide it here in the middle, yeah. So one group and the other group, so like that. And on the left-hand side, you please do the second task, yeah. Design the measurement layout plan to capture the most relevant quantities for the purpose of the test. So you please think about how should this pile be instrumented? What does it need so that we can measure these things which are shown here? What would you do then? Okay, just come up with a plan, and you can also later on. Then I will just open here a whiteboard, and you can just draw your plan, please, here just live on the screen. Okay, so think about that, and please sit together and discuss this. It's not a problem if it gets loud, okay? And the other group, you are a big group. You please do the first one. So there you have to calculate a little bit. So please choose an appropriate model pile geometry, applying the similarity laws P1 and P2 according to this what I've shown you before. Yeah. So you have to think now, and you could even also separate yourself and say, okay, one is doing P1, other is doing P2, and we look together at that. But please really now start with that. And I think we have, yeah, let's give it 10 to 15 minutes, so maximum 15 minutes. Good luck. So if you have any questions,